Morning friends, welcome to week number 4. In the previous 2 weeks, we have discussed about the development of generalized heat diffusion equation in 3 different coordinate systems, and also in the previous week we have talked exclusively about 1D heat conduction equation and its possible solutions primarily in all the 3 coordinate systems, which led to the concept of thermal resistance. And we have seen that instead of solving the equations directly, how can we directly make use of the thermal resistance concept to solve several scenarios associated with 1D steady state heat conduction. However, the primary assumptions that we have taken there were not 2, rather 4. Along with 1D and steady state, we have also considered the absence of any kind of heat generating source and also constant thermal conductivity. Now, in this week we shall be talking about some special 1D heat conduction situations where some of those, particularly the last 2 assumptions, that we are going to relax, but it is still going to be 1D and something not mentioned in the title of this module, that is we are going to deal again with steady state systems only. Now, I am just going back to the generalized heat diffusion equation. While we develop the equations in 2 different coordinate systems, but here I am going to write or rather 3 different coordinate systems. I am going to use only 2 of them here. Cartesian. So, in Cartesian coordinate system we have seen that the generalized heat diffusion equation can be written as dou x of k x dou t dou x plus dou y of k y dou t dou y plus dou z of k z dou t dou z plus the volumetric heat generation, that is q 0 triple prime, plus rho c dou t signifying the time rate of change of energy content of the system that we are dealing with. Similarly, in cylindrical coordinate system we have developed the same equation, again starting from a cylindrical element, an infinitesimally small cylindrical element, and the equation was of the form 1 by r dou r of r k r dou t dou r plus 1 by r square dou phi of k phi dou t dou phi plus dou z of k z dou t dou z plus again the rate of volumetric energy generation and the transient term on the right hand side. These 2 remains unaltered in all the coordinate systems. Now, in the Cartesian coordinate, our coordinate directions were x, y and z, and in cylindrical coordinate it was the radial direction, azimuthal direction and the axial direction z. Accordingly, we have got these equations. Now, here in these equations we have considered, like in Cartesian one we have written k x, k y and k z are the 3 possible values of thermal conductivity, because we know that while for isotropic materials these 3 are equal to each other, but there are certain anisotropic materials which has some direction dependence of the thermal conductivity, and that is why to make it generalized we have included the terms. Now, once we are imposing the first 2 conditions, that is steady and one dimensional, then what we are going to have in Cartesian coordinate, if we remove the y and z dependency, then the equation becomes d dx of k x dt dx plus q 0 triple prime is equal to 0. Remember the last 2 assumptions which we kept on considering in the previous week, that is no energy generation or no internal energy generation and also constant thermal conductivity, that we are not considering. Accordingly, both k x and this q 0 triple prime that remains in the framework. Similarly, in the cylindrical one, if we neglect any variation in the phi and z direction, then the equation simplifies to 1 by r d d r of r k dt dr plus again that q 0 triple prime to be equal to 0. In both the cases for we can drop the subscript for k, because as it is an 1D scenario. So, there is no point considering k having a spatial dependency, just one value of k is sufficient for this. Now, in this week what we are going to talk about is a special scenario where either k can be a variable or qg dot triple prime is present in the system, and it is also possible that both of them, that is the spatial dependence of k and also the heat generation, needs to be considered. Let us talk about the energy generation first. In this lecture I am going to talk about heat conduction, 1D steady state heat conduction with energy generation. Now, what are the possible scenarios where we can have some kind of energy generation present in the system? We have talked about examples like some nuclear material, but another very common source can be an electrical resistor. So, if there is an electrical conductor through which a current is flowing in, then we all know that following the Ohm's law, we shall be having, following the Joule's law, there will be some kind of Joule heating losses. And if the value of the resistor is R, that electrical resistor that I am talking about, and I is the magnitude of current, then corresponding energy generation will be equal to I square into R. This is the total amount of energy or rate of energy generation that is present in your system. And if we want to know the volumetric energy generation, then this energy generation rate needs to be divided by the volume of the system, that is the volumetric energy generation will be E square R electric, that is electrical resistance, divided the volume of the electrical resistor that we are considering. This is the most primary kind of system that you can identify with energy generation, apart from the nuclear materials, which of course has very limited applicability or applicable only in certain special systems. But for the moment we are going to deal primarily about this kind of losses, and also couple of assumptions that we are putting in, which are exclusive for this lecture only. That is, we are considering energy generation, but we are considering that, or we are rather assuming this energy generation to be constant. That is, this qg dot triple prime, in general this qg dot triple prime is expected to be a function of time and all the three spatial directions. As we have reduced ourselves or restricted ourselves to a steady state one dimensional scenario, so we can write this to be a function of x. Now, assuming this constant value of this energy generation, we are considering that this qg dot triple prime is no more a function of x, that is everywhere in your domain it has the same magnitude. And another assumption that we are considering for today's discussion, we are considering the thermal conductivity to be constant. That is, we just want to check the effect of this heat generation first, and then the effect of thermal conductivity or variation in thermal conductivity with spatial location, that we shall be considering in the next lecture. So, first we are going to deal with a plane wall with energy generation. Then the equation that I wrote earlier, we can start exactly from here. So, the generalized version of, let me summarize the assumptions then. We are considering steady state one dimensional heat conduction in plane wall, x is the only coordinate direction of importance. We are considering volumetric energy generation at a constant rate, and also we are considering constant value of the properties, particularly the thermal conductivity. So, the equation that we had written in the first slide, it was ddx of k dt dx plus qg dot triple prime is equal to 0. So, now putting these assumptions of constant thermal conductivity, we can write this one to be d2t dx2 plus qg dot triple prime upon k is equal to 0. So, we have to solve this one now. Remember, this term in the bracket is constant as per our second, third and fourth assumptions. So, it is not very difficult to solve this one at all. We can directly write d of dt dx is equal to minus qg dot triple prime upon k into dx, that is dt dx becomes minus of q dot triple prime upon k into x plus c1, and if we integrate it once more with respect to x, then we get t as a function of x to be equal to minus of q 0 triple prime upon k into x square by 2 plus c 1 x plus c 2. So, this is the temperature distribution that we are trying to identify. With once we know the volumetric energy generation rate and the thermal conductivity, we can get the temperature profile. But of course, to get the temperature profile, we need to have couple of boundary conditions, because there are two unknown constants C 1 and C 2. Let us say at some location, say x equal to x 1, it is given that T is equal to T s 1, and at x equal to x 2, it is given that T is equal to T s 2. So, combining these two, we can write that T at x 1, which is T s 1, is equal to minus of q 0 triple prime upon twice k into x 1 square plus c 1 x plus c 2. Similarly, T at x 2, which is nothing but T s 2, is equal to minus of q 0 triple prime upon twice k x 2 square plus c 1 x 2 plus c 2. So, if we write them together, then T s 1 minus T s 2 is equal to minus of q 0 triple prime upon 2 k into x 1 square minus x 2 square plus c 1 into x 1 minus x 2, which gives C 1 to be equal to okay, let us write the volumetric energy generation term first. So, it becomes then q 0 triple prime upon twice k into x 1 square minus x 2 square can be written as x 1 plus x 2 into x 1 minus x 2. So, divided that by x 1 minus x 2, it just reduces to x 1 plus x 2, and we have T s 1 minus T s 2 upon x 1 minus x 2, which is our C 1. Now, I have to get C 2. So, C 2 we can get by putting the expression for C 1 in any of these two equations 1 and 2. Let us put in 1. So, putting in 1, we have T s 1 to be equal to minus of q 0 triple prime upon twice k to x 1 square plus C 1 x 1. So, what is your C 1 x 1? Q 0 triple prime by twice k into x 1 plus x 2 into x 1 plus T s 1 minus T s 2 upon x 1 minus x 2 into x 1 plus C 2, which gives you C 2 to be equal to q 0 triple prime upon twice k into x 1 square minus x 1 square minus x 1 x 2, which means that x 1 square cancels out, plus T s 1 minus T s 1 minus T s 2 upon x 1 minus x 2 into x 1. So, very big expressions we are getting for both C 1 and C 2. Just simplifying this expression for C 2 one step more. So, we are left with minus of q 0 triple prime upon twice k into x 1 x 2 plus T s 1 minus T s 1 minus T s 2 upon x 1 minus x 2 into x 1. So, you have got the expressions for C 1 and C 2. Let us try to develop the final equation for T. So, T at x now becomes, or originally it was, I repeatedly have to come back to this slide because these are big expressions. So, it was minus q 0 triple prime upon twice k into x square plus C 1 x plus C 2 So, we have to now put the expressions for C 1 and C 2 which we have developed recently. So, the expression for C 1 we are putting first. So, here I am having q g dot triple prime upon twice k into x 1 plus x 2 into x plus T s 1 minus T s 2 upon x 1 minus x 2 into x. So, this is the expression for C 1 that we have developed, and that straightforward way I have put there as C 1 into x, and now the expression for C 2 can go there as well, which is minus q 0 triple prime upon twice k into x 1 x 2 plus T s 1 minus T s 1 minus T s 2 upon x 1 minus x 2 into x 1. Just check whether we have written correctly or not the expression for C 1 and C 2. This one final step is to simplify this entire thing to get in a reasonable form. So, let me write that T s 1 first. Then there are 3 terms I can identify involving that q 0 triple prime upon twice k. So, I am writing that together, taking that together minus q 0 triple prime upon twice k, to inside I have an x square plus x 1 plus x 2 into x and another x 1 x 2 coming from the other side. Just check the symbols. So, this will be negative then, and this will become positive, and the term involving this T s 1 minus T s 2 upon x 1 minus x 2 will have x minus x 1, but x 1 is the initial location. So, not very difficult, but quite long mathematical procedure that we are doing, but what we have done is nothing but starting from this generalized equation and then put this two limits at x equal to x 1 t is equal to T s 1 and at x equal to x 2 t equal to T s 2. One final step then to complete this T s 1 minus q 0 triple prime upon twice k into, what is the best way of writing this? Let us keep this in this particular form only. X 1 plus x 2 into x plus x 1 x 2, and the last term we are rearranging as T s 1 minus T s 2 into x minus x 1 upon x 1 minus x 2. So, this is a generalized equation that we have developed for a simple one dimensional heat conduction scenario through a plane wall, which is being subjected to an uniform rate of volumetric heat generation. Quite often, as in order to avoid, or in an effort to avoid such complicated equation, we go for simpler description of the coordinate locations x 1 and x 2, so that we can reduce the equation to an even simpler form. Just look at this. Here our geometry involves again the heat generation through a plane wall. This wall is kept at temperature T s 1. So, this is our wall x 1, this is the location x 2, its temperature T s 2. In an effort to avoid such complicated expression, what has been done is that the coordinate frame or origin of the coordinate frame x equal to 0 has been selected as the central line of this block. So that now your both the walls are equally located, like locations are shown here. This is at a distance L and this is also at a distance of L from this, and accordingly our x 1 becomes minus L, x 2 becomes plus L and x1 minus x2 becomes minus of twice L. If we are going for this kind of geometric definition, then the equation becomes quite simpler. Equation takes a much simpler form. Let us try this out. Also, I should add here x1 plus x2, then becomes equal to 0. So, if we put this particular form, then temperature at any x location, you have to remember that here the x is defined with respect to that central line. So, any location which is on this side of the central line will be having a positive value of x, whereas any location which is located on this side will be having a negative value of x, and x equal to plus L and x equal to minus L are the two extreme locations. So, in that case what will be your expression for temperature profile? So, it remains Ts1 minus Qg dot triple prime upon twice k into we have x square, x1 plus x2 is equal to now 0, and what is x1 x2? So, x1 x2 is equal to minus L square. So, we have its x square minus L square, and similarly for the last term Ts1 minus Ts2, we have x minus x1 in the numerator. So, it becomes x plus L, remember x1 is equal to minus L, and x1 minus x2 is equal to minus of twice L. So, minus of twice L in the denominator. So, we can rearrange them a bit. Ts1 minus Q0 triple prime upon twice k into x square minus L square plus let us take this 2 inside as Ts1 minus Ts2 upon 2, and also we are taking this minus sign out. So, it becomes x upon L minus 1 for this. So, this is the final form of expression probably we are looking for. Quite often instead of expressing this way, we would like to express in a more convenient form or generally in a more compact form by doing some further substitutions. Ts1 minus, let us take L square out of this, or taking rather L square common, so that we can write Q0 triple prime into L square upon twice k, then it becomes, and writing this as positive, it becomes 1 minus x upon L whole square, or let me change the bracket for easier representation. And similarly from the next one, if we take L common, Ts1 minus Ts2 upon twice L, then it becomes, it just becomes L minus x. Actually, I have made a mistake somewhere in the symbol, it was positive, and so it is again L plus x, and that twice L has come out. So, it remains minus 2L outside. So, this is a closed form equation that we are looking for. Quite often we would like to represent this one, means sometimes instead of expressing this way, we can break the last term even further, like in order to combine the Ts1 and Ts2, rather I should say in an effort to combine this term and this term together, sometimes we separate them as we write the first term Ts1 minus Ts2 upon 2 into x upon L, and the last term we write separately as just Ts1 minus Ts2 upon 2, so that we can combine this one and this one now to leading to the final form that we are looking to develop, Q0 triple prime upon L square divided by twice k into 1 minus x upon L whole square minus Ts1 minus Ts2 upon 2 into x by L, and if we combine the Ts1 minus Ts2 upon 2, then it becomes plus Ts1 plus Ts2 upon 2, which is nothing but the mean temperature of the mean of the two end temperatures. Yes. So, this is the final form that we are looking for regarding the steady state one dimensional heat conduction through a plane wall, which is being subjected to uniform heat generation with constant thermal conductivities. You can easily see that if you put x equal to minus L, this will reduce to T equal to Ts1. If you put x equal to plus L, this will reduce to T equal to Ts2. And what about x equal to 0, the mid plane? So, if we write T0, which refers to Tx at x equal to 0. So, what you are going to get in that situation? Then it will be equal to Qg dot triple prime into L square upon twice k. This is the corresponding to the first term. By putting x equal to 0, the second term cancels out, and then we have this mean as Ts1 plus Ts2 upon 2. This is the mid plane temperature somewhere here as the temperature T naught. And if our interest to calculate the rate of heat transfer through this, then what it will be? Then Q dot conduction will be equal to minus of K A dt dx. So, we can write minus K A into differentiating this one with respect to x, we have Q dot triple prime upon L square by twice k into differentiating the next term, it remains minus 2x upon L square, minus 2x upon L square is corresponding to the first term. For the second term, it remains as Ts1 minus Ts2 by twice of L, and that remains the second term. If we just rearrange it a bit, taking the minus sign out, so we have K A Q dot triple prime L square by twice k into 2x upon L square plus K A into Ts1 minus Ts2 upon twice L, K A by 2L Ts1 minus Ts2, the second term I am writing first, and for the first term, so we can see that k and L square cancels out, the 2 also cancels out. So, we can remove the k, we can remove the L square, we can remove the 2 as well. So, we are left with Qg dot triple prime into A into x. So, how this term is looking like? What about the first term? K A upon twice L. What is twice L? Twice L is a length scale associated with the heat transfer direction, because the distance from the wall at location minus L to the wall at location plus L is actually 2L. So, K A upon 2L, or rather opposite of that, 2L upon K A is something similar to the thermal resistances. So, the first term that you are getting here is nothing but the heat transfer that we could have derived from thermal resistance, or using the resistance concept. By using a constant thermal conductivity of K and a length scale of 2L, we should have got this one. But here we have an additional term in the form of this Qg dot triple prime A into x, which is coming because of this volumetric energy generation. And also it is important to note that there is an x present in the last term, that is the volumetric energy generation. Because of the presence of volumetric energy generation, the heat transfer rate is not constant, rather it is a function of x. At x equal to 0, it will be equal to 0, that is at the central line heat generation will be equal to 0, but as we move away from this, you will be having an increased contribution coming from the second term. And also this term Qg dot triple prime into A into x, what is the physical significance of this? A is the cross section area, x refers to any distance. So, if we have, say, at this particular distance, we want to calculate the amount of energy conduction or contribution to energy conduction coming from this term, that basically will lead to the volume corresponding to this portion. So, I should have drawn the entire volume. The A into x refers to this entire volume, because A is the cross section area and x is the distance, and whatever volumetric energy generation is taking place inside this multiplied by this corresponding volume contributes to this second term in energy production or energy transmission, I should say. Now, one special case we could have had, I should just repeat the term, the entire expression for T x that I have got. T x is equal to, I had this one, q 0 triple prime into L square by twice k into 1 minus x upon a whole square minus T s 1 minus T s 2 by 2 into x upon L and T s 1 plus T s 2 upon 2. So, this was the expression that we had. Now, if we consider a special scenario something like this, where at both x equal to plus L and minus L, we are having the same temperature T s. The temperature is same at that location T s. Then what we should have, here we are talking about your T s 1 and T s 2 both are equal to T s. Here the system is being subjected to symmetrical boundary condition. In the previous case it was asymmetric, and look at the temperature profile that we have got here. It is an arbitrarily drawn temperature profile, of course, but the temperature profile that we have got here, that shows that assuming T s 1 to be higher, we are having a parabolic kind of nature, because we are having an x square term present, but this parabola is not symmetric with respect to the central line. So, as T s 1 is higher than T s 2. But now we are having a geometry where T s 1 and T s 2 both are equal to T s. Then in that case, what will be the temperature distribution T x? Your T x in this case is going to be, the first term remains unaltered, q 0 triple prime L square upon twice k into 1 minus x upon L whole square, but the second term T s 1 minus T s 2, that cancels out, and the third term reduces to T s, which is a perfectly parabolic profile. That is what we are getting. The base value is T s, and then we are having a parabola on top of this. Now, at which point this temperature profile is going to have its maxima? To get that, let us calculate dt dx and assign that to 0. So, we are going to have q dot triple prime L square upon twice k into, differentiating this, we have minus 2x upon L square rather, to be equal to 0. Now, simplifying this, as L square and 2 cancels out, we have minus of q 0 triple prime upon k into x to be equal to 0. Now, q 0 triple prime can't be 0, because there is a volumetric rate of energy generation. If there is no energy generation, then there are two things we can identify. If k can't be 0, because k is the thermal conductivity, a property of the system, it can't be negative as well, it is always a positive number. Now, if there is no volumetric energy generation, then the entire temperature profile in that case T x becomes equal to T s, only if q 0 triple prime is equal to 0. That means, throughout the system you have the same temperature. And secondly, if q 0 triple prime is having a non-zero value, in that case the maxima will appear at x equal to 0, that is only at the center line. So, this is the location where you are going to have the maxima of this temperature, and this maxima T naught, that is T at x equal to 0, which you can also write at the maximum temperature for this system, you can easily obtain by putting x equal to 0 in the expression, which will be coming as T s plus q 0 triple prime into L square by twice k. So, this is the maximum temperature you can identify, and we are getting an uniform temperature distribution. Now, what about the rate of heat transfer? In the previous case, we developed the rate of heat conduction like this. Let us try to develop the expression for rate of heat conduction in this situation as well. So, here q dot conduction will be again equal to minus K A dt dx following Fourier's law of heat conduction. So, what we are having here, just differentiating the above expression, we have minus K A q dot triple prime into L square by twice K into minus of 2x upon L square. So, minus cancels out, we can remove that K and that 2 L square everything. So, it comes out to be q 0 triple prime into A into x. So, in the previous expression, look at this, here the expression for q 0 triple prime that we got, there was a constant term and then we had that q 0 triple prime A into x, and that constant term was appearing because of the difference between these two end temperatures. Now, as the end temperatures are not different, in that case we are not having that first term, and therefore, what will be your conduction at x equal to 0? That is going to be 0 only. So, that means this mid plane, this particular plane is not having any heat transmission across this, it is acting like a plane of symmetry. Whatever heat conduction taking place on this side, the same amount of heat conduction is taking place on the other side as well, there, so that net heat conduction is equal to 0, it is acting, and the temperature profile across the central line is going to be mirror image like this, temperature profile on either side will be mirror image of each other. So, the central line can be considered to be a plane of symmetry, and therefore, this central line we can almost assume to be like an insulated surface, just like this. We can just do the analysis for half of the domain, and whatever we are getting the solution, we can easily extrapolate that to the other side. Therefore, if we are having a plane of symmetry like this, you could have easily solved the problem by putting your boundary condition at x equal to L to be T equal to T s, and at x equal to 0, the rate of heat conduction is equal to 0. So, that dt dx is equal to 0, which is the symmetry boundary condition that we can very conveniently use in several scenarios, as long as we are having a symmetrical temperature profile like this. Now, one final thought on this, quite often we may not be knowing the end temperatures Ts1, Ts2 or the Ts in this case, they may not be knowing, and to identify that we may have to use the information available outside the block, like in shown here, the block may be subjected to some kind of convective heat transfer, and therefore, we can easily make use of the balance between conduction and convection at the surface under steady state condition. So, that the conduction heat flux at x equal to plus L should be equal to the convective heat flux again at x equal to plus L. So, what is your conduction heat flux? That is equal to minus K into dt dx, and corresponding convective heat flux will be equal to heat transfer coefficient into the surface temperature T s minus the free stream temperature T infinity. Expression for dt dx we have developed. So, putting there you can easily get the if we have knowledge about T infinity and H, you can easily identify T s from here, and subsequently you can incorporate that into your analysis, because if we want to get an closed form expression, in this case let us quickly complete this. So, dt dx we have done earlier also, and therefore, in this case dt dx at x equal to L comes to be equal to q g dot triple prime into L is equal to H into T s minus T infinity, giving you T s equal to T infinity plus q 0 triple prime into L upon H. So, the same way we can calculate the value on the other surface if the temperatures are different. So, this way by using very simple mathematical manipulations, we can also consider uniform rate of heat generation, but of course, we have considered rate of heat generation to be uniform only. If that is non-uniform, then we may have to depend on some other techniques, the calculation will become much more complicated. Let us quickly check the scenario with a plane cylinder. So, for plane cylinder, this is the geometry that we have. We are having a cylinder like this is the center line of the cylinder, and this let us say the radius of the cylinder is capital R, this is your radial direction, and length of the cylinder may be L. So, we have to calculate or we have to get an expression for the temperature profile when the cylinder is experiencing uniform heat generation inside this. So, we have already seen the basic equation can be written as 1 by R ddr of R k dt dr plus q 0 triple prime to be equal to 0. Taking thermal conductivity to be constant, then we are left with 1 by R ddr of R dt dr plus q 0 triple prime upon k equal to 0. So, d of R dt dr plus q 0 triple prime upon k into R dr. Remember, here you are taking q 0 triple prime and k both to be constant. So, accordingly, after one step of integration, we have R dt dr plus q 0 triple prime by twice k into R square to be equal to 0. So, we have dt plus q 0 triple prime by twice k into R dr is equal to 0, which gives after next integration T R, actually after the first step of integration I should have got the constant of integration somewhere as C1. So, it becomes C1 dr, and after doing this, then I can write this to be equal to q0 dot triple prime upon 4k into R square plus C1 to be dr by R. Then accordingly, it becomes C1 into log of R plus another constant C2. So, you have to identify them. Now, before proceeding, just check at this particular situation at R equal to 0, then if dt dr, the temperature gradient has to be finite, then C1 has to be equal to 0, because at R equal to 0, if C1 is equal to 0, then only dt dr will be equal to 0. Otherwise, dt dr what we are getting is here dt dr is equal to C1 by R. So, to have any finite value of this, only possible scenario is C1 equal to 0. So, then one we can directly eliminate from this q 0 triple prime upon 4k into R square plus C2. Second boundary condition is quite straightforward. Let us say the surface temperature is Ts. So, at R equal to capital R, T is equal to Ts. Accordingly, T at R is equal to Ts minus q0 dot triple prime upon 4k into capital R square. So, I should have written Ts is equal to C2 minus this, giving you C2 to be equal to Ts plus q dot triple prime upon 4k into R square. So, taking it back here, T R is equal to then Ts plus q dot triple prime upon 4k into R square minus small r square, that is equal to Ts plus q dot triple prime into R square by 4k into 1 minus small r upon capital R whole square, which is the closed form solution that we could have got about temperature profile within this plain cylinder subjected to heat generation. We can easily calculate the rate of heat conduction at any location here. So, q dot conduction, okay, before that if we want to calculate the center line temperature T naught, that is T at R equal to 0, you can easily put it R equal to 0 in this expression to get Ts plus q dot triple prime into r square by 4k, that is going to be your T naught. And therefore, sometimes we also write this expression in an alternate form as T s plus T naught minus T s into 1 minus smaller by capital R whole square. That is another form we could have easily written this. Now, what will be a rate of heat conduction? Then q dot conduction will be equal to minus K A dt dr, that is minus k at any r location, it will be equal to 2 pi r into L, L being the length of this particular cylinder, L is this dimension that I am talking about, into dt dr. So, how much is your dt dr? That is equal to q 0 triple prime upon 4 k into minus of twice r. We could have easily written this one in T naught minus T s also in that term. So, it becomes now positive k into pi r square L q 0 triple prime upon k. In fact, k also cancels out. So, I should have written this one as q 0 triple prime into pi r square L. Again, pi r square L refers to the volume of an incremental cylinder. If we take an n incremental volume inside, pi r square L will be the total volume of this. Then how much is the total heat generation? So, or at the surface, maybe q dot conduction at r equal to capital R, means total energy conducted at the surface at this location, that refers to the surface of this cylinder. So, it becomes pi r square L, that is the entire volume of the cylinder into the energy generation, that is the amount of heat that will be coming out. And if this cylinder is subject to some kind of convective boundary conditions, say a fluid with temperature T infinity and heat transfer coefficient of H, then this should be equal to q dot convection, which is nothing but H into total surface area. How much is the surface area? Remember, conduction and convection both in this case is happening on the surface area, the peripheral area, which is 2 pi r into L into the temperature difference T s minus T infinity. So, using this we can also get an expression for T s from this, if T s is not known. So, this way we can take care of energy generation inside both plane wall and plane cylinders. Now, let us quickly solve couple of numerical problems to get a taste of what we have done. First problem involves, okay, before solving any problem, one thing you have to be careful, the resistance concept that we have used in the previous week, that is not applicable when energy generation is present, because when energy generation is present, we have seen for both, in case of both plane wall and cylinder, that the rate of energy conduction is a function of x and a function of location, I should say, and as it keeps on varying from one point to another in the same system, therefore, we can't go for the resistance concept, we have to stick to the basic formulation. However, if your system can be broken into several components, where some component is experiencing energy generation and some components are not, then for the components where there is no energy generation, you can still stick to that resistance concept. That is precisely what we are going to check in this first numerical problem. Here it is given that we are having a plane wall which is made of two materials A and B. The wall of material A has uniform heat generation and a thickness of 50 millimeter, and wall of material B is having no heat generation and thickness of 20 millimeter. So, you can draw the walls maybe. So, we have two blocks, this is your A, this is your B. Block A is having thickness of L A, block B is having thickness of L B. Here, as per our given information, L A, the thickness of the first block is 50 millimeter, that is 0.05 meter. L B is equal to 20 millimeter, 0.02 meter. Their thermal conductivities are given also. K A is equal to 75 watt per meter Kelvin, K B is equal to double of the previous one, 150 watt per meter Kelvin. The wall A is having energy generation. So, Q0 triple prime for A is given as 1.5 megawatt, that is 1.5 into 10 to the power 6 watt per meter cube. No heat generation in the second one, that is layer B. Now, the inner surface of material A is well insulated. So, this side is well insulated, no heat transfer across this, while the outer surface of material B is cooled by water stream with 30 degree Celsius and H equal to 1 kilowatt per meter square Kelvin. So, on this side you are having a fluid flowing with temperature T infinity and heat transfer coefficient H. It is given that T infinity is equal to 30 degree Celsius, that is 303 Kelvin, and this convective heat transfer coefficient is 1 kilowatt, that is 1000 watt per meter square Kelvin. You have to determine the temperature of the insulated surface and the cooled surface. So, let us say temperature at this point is T0, temperature at this point is at this surface is Ts. This we have to calculate. So, there are two layers, and therefore, and as we are having heat generation only in one of the layers, so we can treat the layers separately. For layer B we can use the resistance concept, but for layer A we have to follow the mathematical approach that we have just done. Now, for layer A, as there is heat generation, so here Q dot will be a function of x, but layer B, as there is no heat generation, there is no heat Q dot will be a constant in this case. Then let us try to tackle QB and write an energy balance at this point. What we can write there? At that point Q dot conduction should be equal to Q dot convection. Now, conduction should be equal to minus K A dt dx, which is equal to the total heat transmitted through this is equal to H into area into, actually Ts refers to the temperature of this surface, this one that we have to calculate, Ts minus T infinity. Let us say the temperature at this point is TAB. We have to find the temperature of the insulated surface and the cooled surface. So, Ts is the temperature, and this is why we can write this, write the energy balance at this surface, at the cooled surface. But how can we get this Q dot? From where the Q dot is coming? The Q dot is coming because of whatever energy that is getting generated in A, that is passing through B without any change. So, total energy generation or heat generation, I should say, within A, that should get transmitted through B as it is. So, this is the Q dot that I am looking for, and that should be written as QG dot triple prime into the volume of this block A, which is nothing but cross section area into L. Now, in this case Q dot triple prime is given as 1.5 into 10 to the power 6 into cross section area is not given, L A is equal to 0.05. So, we can easily calculate the total value of Q dot, and once we take it back here, then we have an estimate of Ts as equal to T infinity plus Q dot upon H into A. So, T infinity in this case is 303 Kelvin plus Q dot we have got to be 1.5 into 10 to the power 6 into that area into thickness of block A, and convective heat transfer coefficient here is given as 10 cube into A. So, if you calculate the numbers, the temperature at this point at the cooled surface is going to be about 378 Kelvin, which is about 105 degree Celsius. So, this is one of the solution, this is for the cooled surface, which you can get very easily. Now, we have to do for this surface number B. What about the temperature point TAB? How can we calculate TAB? If we talk about energy transmission via resistance, in the following the electrical resistance concept through the layer B, then we can express it something like this. Here your temperature is TAB, here the temperature is Ts, which you have just calculated, and how much will be this resistance? It should be equal to L by LB by, it should be equal to say R thermal for layer B. R thermal for layer B is equal to LB by thermal conductivity of layer B into A, and it is having that Q dot going through it, and therefore we can write that TAB minus Ts divided by Q dot is equal to R thermal B, which is equal to LB upon KB into area. So, TAB is equal to Ts plus Q dot into R thermal into B. Ts we have now calculated to be equal to 378 Kelvin plus Q dot is 1.5 into 10 to the power 6 into area into 0.05, and R thermal is thickness of layer B to be 0.02 by its thermal conductivity is 150 into the area A, and accordingly it cancels out. So, we can easily get the temperature at that particular location. I do not have the numbers here for this TAB, you please try to do the calculation to check whatever values you are getting in this particular case. Actually, it will not be very difficult to get. If we try it out, it is 378 plus what we have? We have 15 into 10 to the power 5 and then 5 into 2 into 10 to the power minus 4 and 15 into 10 in the denominator. So, accordingly it remains to be 378 plus 15 and 10 both cancels out, and it just 10 leading to 388 Kelvin, that is 115 degree Celsius, that is TAB. And once you know TAB, then you can easily go back to the earlier approach that we have done to get the values of the T naught. If I just go back to this surface plane wall with heat generation, this was the temperature profile that we had in this. So, you can easily follow this approach to get the temperature at the other end. Here in this case we are looking to identify the TS2 itself, and TS1 is that TAB that we have just got, and accordingly you can do the calculations to get the final result. So, final solution for T naught is going to be equal to 140 degree Celsius. You please do the calculation to see whether you are going to get the results or not. Now, a second problem I would like to quickly go through this one. Here the problem involves a nuclear reactor which incorporates cylindrical fuel rod of 25 millimeter diameter. It is made of thorium which is having thermal conductivity of 60 watt per meter Kelvin, and it is wrapped in thin aluminum cladding. It is proposed that under steady state condition the system operates with a uniform heat generation rate of 700 megawatt per meter cube, and its fuel rod and it should be the fuel rod is cooled by a stream, and the fuel rod is cooled by a stream maintained at 95 degree Celsius and corresponding H is given. So, you are having a thermal you are having a cylindrical fuel rod. Let us draw only half of the domain. So, this is your fuel rod made of thorium, and around this rod we are having a thin cladding. Cladding is nothing but a jacket kind of thing. So, this is the fuel rod, its diameter is 25 millimeters. So, radius is 25 by 2, and an aluminum cladding, it is a very thin aluminum cladding. So, the cladding thickness is not given, which can be neglected for the situation shown here. We can almost assume that the surface is made of this aluminum surface is just like this aluminum cladding. So, we are not going to draw the cladding surface separately, rather this is the half of the domain that I am considering, half of the cylinder. There is heat generation that is happening inside the cylinder, and outside we are having a fluid flowing with temperature T infinity. In this case T infinity is set at 95 degree Celsius, that is equal to 368 Kelvin. Corresponding convective heat transfer coefficient is 7 into 10 cube watt per meter square Kelvin. So, you have to solve this problem. Again there is a heat generation part. So, using heat generation, let us try to calculate the temperature T naught here and the surface temperature T s here. You already know the expression, the way to derive the expressions for this. For the moment you just neglect the cladding, just consider this is a cylinder and which is having uniform volumetric heat generation. You have to calculate this temperature T naught and T s. So, what will be T s? Just performing and balance between conduction and convection here. So, we know that the total amount of energy coming via convection or being lost to convection is equal to H into area, which is 2 pi into radius r into length of the cylinder L into T s minus T infinity, that is equal to total amount of energy generated inside this, that is q 0 triple prime into pi r square L. So, we have T s is equal to T infinity plus q 0 triple prime into pi r L cancels out. So, we are having an r left there and we have twice of H here. So, putting this, you already know the value of T infinity, which is coming to be 368 Kelvin. Q 0 triple prime in this case is given as 700 into 10 to the power 6 watt per meter cube into radius is 25 millimeter. So, it is going to be 12.5 into 10 to the power minus 3 millimeter, 2 into convective heat transfer coefficient is 7 into 10 cube. So, if you do the calculation, T s in this case will be coming as 993 Kelvin. Now, you have to calculate the value of T naught, and T naught we have seen that is going to be T s q dot g into r square by 4 k. So, T s we have got to be 993 Kelvin plus generation is 700 into 10 to the power 6 into 12.5 into 10 to the power minus 3 whole square by 4 into thermal conductivity of thorium, that is 60. So, the thermal conductivity of aluminum actually never coming into picture, because aluminum layer we are not considering anywhere during the calculation. So, this T naught is coming to be equal to, I have just got the final number 1449 Kelvin. So, the temperatures we have identified, this is the maximum temperature the system is having, this is the temperature at the surface of that aluminum cladding basically. You have to judge whether this proposal is valid or not. The proposal is valid or not, that depends upon the melting point. See, the melting point of thorium is 2023 Kelvin and the maximum system temperature is well below that. So, the thorium will remain in solid, but the melting point of aluminum is 933 Kelvin and we are having the surface temperature to be 993 Kelvin, which is going to be the aluminum temperature. So, aluminum is going to melt if we run this system. So, this cladding will not be able to stay and hence this proposal is not valid. If we want to make the design valid, then there are several ways we can make modification. One way is if we reduce the volumetric rate of heat generation, but that depends upon the rate of fission reaction, and also we always want higher volumetric energy generation in such kind of systems. Then another possibility is if we can reduce the radius of radius of this rod, so that the surface temperature becomes smaller. Another definite possibility, if we can increase the heat transfer coefficient H, but again that depends upon the coolant side conditions. And of course, if somehow we can use a cladding material which is having a higher melting point, that is also very much possible. Finally, I would like to give you another example of a scenario where we have heat generation or rather conduction with heat generation, that is inside our body only. You know that because of the metabolic activities our body is always converting chemical energy to thermal energy, and that thermal energy is going to get conducted through the tissue to our tissues, come to the skin, and then that get dissipated to the surrounding via convection. But before it reaches the skin, it is only conduction and conduction with energy generation, and that is where the bioheat equation comes into picture. It is nothing but the thermal conduction equation modified to incorporate the metabolic heat generation inside our bodies. For the bioheat equation generally can be written in a form as like the earlier equation that we wrote, that was a form like this, q0 triple prime upon k equal to 0. Now, here this q0 triple prime generally can have two contributions. One contribution coming from the metabolic activities and other contribution is coming from the perfusion. Perfusion refers to as the blood flows through the tissues, then it exchanges heat with that. Depending on the temperature of the blood is higher or temperature of tissue is higher, this q dot p can be positive or negative, but the q dot m is always positive. Q dot m, we have standard charts available, like when a person is sleeping, generally Q dot m is in the range of 75 watt, or rather total body generates heat in the range of 75 watt, whereas here we are writing in per unit volume sense. So, that 75 watt needs to be divided by total volume of our body to get the value of this q dot m triple prime. When someone is swimming, it goes in the range of 200 to 250 watts. So, when someone is playing some high activity sports like tennis etc., it can be in the range of 400 watts as well. But q dot p is the one that needs some attention, and without going into detail I shall be giving you the expression that was generally developed, by Pennes. I would like to check the spelling of this because I do not want to write the spelling wrong. Yes. Okay, it is Pennes, it is credited to Pennes. He proposed that this q dot p triple prime can be expressed as omega into rho b into Cb into Tb minus Tt. Here Tb is the temperature of the blood, Tt is the temperature of the tissue, rho b and Cb refers to the density and specificity of the blood, and omega is the rate of this perfusion. And generally omega into rho b can also be considered as the mass of the tissue that is concerned in this heat transfer. So, if we put this form, then the heat conduction equation can be written as like this to be equal to 0, and this is precisely what we refer as the bioheat equation. Generally we used to go for some kind of non-dimensionalization by introducing a term theta. Theta is defined as T minus this Tb minus q dot n triple prime, means before defining the theta, let us just take this term out, this omega rho b Cb. So, that we have omega rho b Cb upon k q dot m triple prime omega rho b Cb into Tb minus Tt to be equal to 0, or this Tt is actually the temperature that we are trying to identify, because this tissue temperature is the one that are objective. So, let us drop the subscript Tt. So, then we can write this one as Tb minus T minus Tb minus q dot m triple prime into the entire part that we just had, q dot m triple prime by omega rho b Cb. If we use this definition of theta, then this equation can be modified to a form d2 theta dx2 plus or maybe minus of m square theta, where this m square is associated with this omega rho b C b into k is to be equal to 0. So, this is the bioheat equation or the Pennes equation often known as. This can easily be solved again using the standard boundary condition, and we can get an idea about the temperature profile inside our body from the coat to the skin using suitable boundary conditions. But I am not going to the deep of this. If any of you are interested, you can just refer to the book of Incorporated and David, the recent versions, where some more information about this is available. So, this is where I shall be stopping today. Today we have talked about the heat transfer with heat generation in both in the plane wall and the plane cylinder. Several scenarios of that has been discussed, like symmetric temperature profile, asymmetric temperature profile, the condition of a symmetrical surface or symmetrical boundary condition, and then we have briefly discussed about heat transfer in biological systems. So, that takes us to the end of our discussion for the day. There is one more lecture this week where I shall be talking about some other special scenario like variable space thermal conductivity during heat conduction. Thank you very much.